Lesson video for 6-2 Day 1. We're going to take everything we know about the rectangular approximations we've been using to get area under the curve that represents that net sum or that net change in a quantity, and we're going to change that into the calculus today. So a little notation back from when in Advanced Algebra Trig you did series and sequence, and a series meant that you were adding together the numbers from a sequence. And when you did that, you were using the sigma sign as your summation symbol. And the things you had to know in order to do that are very similar to the things you had to know to do your right rectangular approximations or all those different ways we were trying to get areas under the curve. Is you had to know an interval where we were starting our lowest x value and our highest x value from, so that we had a definite part of the graph that we were talking about trying to get sums for. You also had to know what formula was generating the numbers that you needed, and that formula for us recently was base times height in order to calculate those rectangles. So just so that we get back in that idea that there's two different kinds of sums. So the first kind of sum would be called a finite sum. And this finite sum tells us that it wants us to go from x is 3 till x is 6 and find those term values and add them up. So when k is 3 for this first one, the formula that generates the sequence I'm adding up is twice the k or index number, so the first value in that sequence would be a 6. And then we would continue to add to it the values in the sequence for each next value, a lot like we continue to add the areas of the rectangles into our totals. So it would go 6 and then we'd have 8. The next term would be 10, and the final term would be 12, and then our sum would be 36. So this notation the value would be 36. This is a definite set of values that we're adding up, so this is a finite sum. There is a measurable or countable number of things going into here, and it comes out to a single number, and that's what that finite means, is there is one final number I can give you that is the sum of all these things put together. We move over here, and some people think the reason that this one won't be a finite or definite number that I can put is that it's going to infinity, and that's not true. What you learned in doing your infinite series last year or the year before was it's not making it go to infinity that means it couldn't add up to a single finite number. But the problem with the function that's in here at the moment is this function 2k does not converge. This function 2k continues to grow, so that as you put in larger k's, you're adding larger numbers to the sum, and therefore there is no final number that this approaches as we add in all those values. It would actually be heading towards infinity. There are, for this type of summation, there are functions where you do have a final finite sum, even though you're adding the terms up to infinity. So you guys learned last year that if your sequence of values converges towards a single number, that then that series would be a finite, have a single value answer. But if this sequence of numbers does not converge, as ours wouldn't, because it would be 0, 2, 4, 6, 8, 10, it's not heading towards one number, then when it won't converge, there is no finite answer to that. There is no one number you can say that that sum would equal. And we're going to have that same thing to consider as we do our integrals. But to take it back for a minute, we've been doing Riemann sums, and what our goal is to find actual sums of area to see what would happen in the limit. And you've done that with GeoGebra, having it make more rectangles for you, and you've done that with your computer program or your calculator program. What we want to do is think about what's actually going on in there. We are adding together the total number of rectangle areas and getting a sum. So in those, we're letting delta x means change in x. That means the length of our subinterval along the x-axis. That's serving as the base for all of our rectangles. And as you've made those rectangles, and you make that base shrink smaller and smaller and smaller, you get more and more rectangles. The sum, and that's what this says, the sum of all your f of something values, and if you've been writing out your work correctly, you know what I mean, that you have one whole quantity that's adding up a bunch of function values. And those function values have been the y coordinates that serve as the heights for all your rectangles. And we have often put them in, if our intervals are the same size, we then have often put the interval width out front multiplied by all of those heights added up to shortcut having to write out the base times the height for each one of the rectangles that we've been doing. If the rectangle base sizes are different sizes, then you'd need to multiply separately the base times the height for each rectangle. But if we have equal subintervals, Riemann's sums, if I put that into sigma notation, the sum of all of my n rectangles would be, and there's a limit in here because we're saying as the bases shrink towards 0, your number of rectangles is going to head towards infinity because you will get more and more of them. And we would multiply together, delta x is our base, change in x, and the sum of all of our heights. So this would be the summation notation for what you've been doing lately. And if this limit exists, no matter how we split up or break into rectangles, then the function has that definite integral we were referring to yesterday. And so we'd call it that it's able to be integrated. There is an integral value, so it's called integrable. Much in the same way we said that if a function is able to have its derivative taken, it's differentiable at points. This page is a box from the book. It's just a definition from the book, and it says exactly what our last page said. Let f be a function defined on a closed interval. So we're speaking of a particular portion of a graph. For any partition of that interval, so we're talking subintervals, let the numbers be chosen arbitrarily, meaning I could break up how many subintervals I would like into as many as possible. If there exists an integral, no matter how we break it up, then we call it integrable, able to have that definite integral found, that final number that will represent the sum of all the changes that we're adding up. Theorem 1's an existence theorem. It just promises us that if a function's continuous, then we can integrate it. All continuous functions are able to do this. So if a function is continuous from an interval a to b, then I can, using either Riemann sums or the calculus that will do, I can find a single value that will represent the net sum, so net meaning of all these areas between the curve and the x-axis. It doesn't say anything about functions that aren't continuous, but here's what we know. There are some discontinuous functions that you can also have an integral for. So we don't want to assume that that's telling us anything else. This was the one, or similar to your warm-ups. Some discontinuous functions are also able to have an integral taken on intervals of it, just like we did for warm-ups yesterday on these greatest integer function. Notation-wise, we're more familiar with summation notation that we just saw. That limit of the sum of all the heights times all the bases would be that sum that we're looking for. And that's what Riemann would have written because he used Greek letters in his notation. Leibniz, who's the kind of one of the two fathers of calculus that they would credit for big branches of it, he used Roman notation. We hinted at this the other day that instead of that sigma, he's using this kind of stylized, stretched out S-looking shape, and that's our integral sign instead of our sigma. Lower bounds and upper bounds, so the lower limit of integration and the upper limit of integration then are just written a little bit to the right below and a little bit to the right above that integral symbol. We have to know what function we're using as all of our heights for those rectangles that we're adding up, so the function's called the integrand. And the reason that they don't put the sigma in there is they're saying that when you add up every single height from every single rectangle and take that limit, every single f of x value is actually represented. And dx, that's our variable of integration. It tells us what we're referring to, but you can also think of it as that's our delta x from up here, and there's our function for various input values. So if every single value of x is input into there, so you can think of that as your base times height, how this ties back to your Riemann rectangles. So all of those rectangles that we were doing, we're trying to estimate the value of this integral for different functions. So when it says that you've evaluated the integral, you found that finite number that's the total of all the things you're adding together. So at first they're going to just ask you to change notation. They're going to ask you to take some of that Greek letter notation and limit notation and switch it over to definite integral notation. Definite integral means that we're looking at it from 1 to 4. We're not looking at it from negative infinity to to positive infinity. We're looking at it in a specific interval. So I'm going to switch that over to being the integral symbol. That will take care of talking about the limit of the sum, okay? And then two things, what our function is, our integrand, and then our variable of integration. So 1 over every single one of those subintervals, so 1 over every single x interval, dx is our variable of integration. And that's all you need there. They want that written as a definite integral, and that one is. They're not asking you to evaluate it, they're just asking you to change notation. So pause the video, try this one out with sign, and see if you can get that correct definite integral notation, and then come back. If you're back, it's to check. Okay, notice my lower bound and my upper bound are in there. Okay, and I'd be looking at sine cubed of x dx. So putting this together with everything we've seen so far, so that we put the notation together with the areas and things that we've been doing, the definition for area under a curve is actually talking about whether or not the area is considered positive or if it counts in the sum as negative. So this first part said, if our function f of x is non-negative, that means it stays at or above the x-axis for an entire interval. So it could even start on the x-axis, but it never goes below, it's non-negative. So then the area between the curve and the x-axis that we would find is the exact value of the integral. So it's telling me that the area here would be the integral value that we're looking for. That's if all of the area is positive, if all of my change is in one direction, okay, in the positive direction. If, and this is the second part, if all of my function is below or at the x-axis between my two values a and b, if everything is either touching 0 or is actually a negative function value, then it's saying between a and b, my area, which would always be positive, but this would be considered negative in the sum because it's all happening below the x-axis. So it's telling you the area would be the opposite of the integral. So if the area is 10, the integral would be negative 10, representing that it's all happening in the opposite direction of whatever your rate function represents. So area is always positive. If the area is above the x-axis, the area is that integral value you're looking for. If the area is below the x-axis, then you'd have to say that it's the opposite of what you're looking for that integral value. So we said they tell the net sum. That means the positive areas count as positive, the negatives count against the total and make the total smaller. So they're going to ask you to evaluate some basic integrals, going back to the idea that you know that area under the curve can be used to get those values or to approximate those values so far. So for this first one, they're switching over to definite integral notation. So they're asking us for this constant function. The function is, that my integrand is the function y equals negative 10. That's a constant function. And they're asking me to find the total sum of everything that happens between x is 0 and x is 3. And because we know that at a constant rate times our change in time is going to be the total effect of what's happening here, so our area, if we were calculating it, our area would be a rectangle that's 3 by 10. Because of area, we don't worry about direction. But our integral value from 0 to 3 for that function is actually going to be negative 30 because that function's entirely below the x-axis, so its area is actually counting as the opposite direction or the opposite meaning, and so our integral value will be negative. The next one, they're giving you another function, and it's another constant function. And they're talking about between an x value of square root of 3 and square root of 27, they would like the integral value of the function pi. Well, pi is a constant, so if my integrand function is pi, there's my constant function. So really, I'm looking for that area under the curve, and that area, because it's above the x-axis, is the value I want for my integrand. So my integrand actually is the same as my area. My area here then would be my base length times my height. My base length would be square root of 27 minus square root of 3. My height would be pi. Square root of 27 is also 3 square roots of 3. So my final value here is going to be 2 times the square root of 3 times pi. And I'm just going to bring the pi out front. That will be my total integral value because it is the area above the x-axis, so my integral is equal to the area. The next two you have use graphs. Okay. And when they use the graphs, they're expecting you to understand that the area above x-axis and the area below the x-axis, if calculated, would be the same as your integral value. So in this one, they're asking us from pi to 2 pi over that interval for the function y equals theta, your integrand, with respect to theta. And if the theta is making you a little uncomfortable why this isn't a constant function, let's switch our thetas to x's for a minute. Okay, the variable here is matching the variable of integration. So that function is saying that y equals x or y equals theta, and it's that red line that I've got graphed. And they would like its integral value from pi to 2 pi. We're not going to do Riemann rectangles here, we're just going to do one trapezoid. The area is exactly what we need for this integral, and therefore if we calculate the area, it's all above the x-axis, we'll have the value we seek. So in this trapezoid, it's going from pi to 2 pi, so its height for my trapezoid then is pi. These individual bases then are what I need lengths for, so I can do my trapezoid area formula. This ordered pair in the function y equals theta would be pi pi, so the height of this side is pi. This one would be input 2 pi, and it outputs you right back to where you are, so my other base is 2 pi. So area for my trapezoid, 1/2, sum of my bases times the height. So we'd be looking at 3/2 pi squared for our integral value. So 3/2 pi squared, and that's my exact value for that integral. The next one over is looking at a semicircle. I'd pause the video, see if you can interpret that area and get a good integral value, and then come back and see how you did. I would know even without a calculator graph that that one's a semicircle because it came from that function, and that equation would be, not function, that equation would be a circle, and if I solved it for y, I would end up with plus or minus the quantity quantity square root of 9 minus x squared. And so I know I only have the positive part of this, so I only have the upper half of the circle. So as I look to do this, they're interested in the area, because it's all above the x-axis, from -3, the net change in area from -3 to +3. So if I find the area of that semicircle, I'll have this integral value that they seek. So in the ones that they're asking you to do in homework, you've got area or ways that you have done already to get that integral value, but you may have to think a little bit about whether or not they count as positive or negative in that net total. So for my semicircle, my area is 1/2 pi times my radius squared. So my integral value then here is 9/2 pi. Finally, in order to check some of these and see how you're doing, you have a way to approximate numerically those integral values. Again, this is not a thing where you can say, oh, well, if I have my calculator, I don't have to know how to do this. This is not something that would serve as any advantage other than being able to check and to get numerical integral values for functions that are harder than the ones they'd expect you to be able to do without one. So under your math key, option 9 gives you that integral function. And when you select that option, it should, if your calculator is updated, give you that integral and be ready. So you could go back to the ones we just did with the graphs, enter those functions and make sure to just practice with that feature. And then come try this one. Okay, and so the function you'd be entering is your integrand. So therefore, when we want to find the approximate area enclosed between the x-axis and the graph from x is -1 to 3, okay, we might want to go look and see if the entire area is positive for that graph, okay, or if the entire area is negative for that graph, because this is going to give us the net sum. So I should probably say net here. The net area enclosed between the x-axis and the graph from -1 to 3. So it's asking us to do an integral from lower bound of -1 to +3. You'd enter your integrand, and you have to enter your variable that you're actually integrating with respect to. Press enter and it will give you an approximate, and it's doing that based on Riemann rectangles and some of the other methods that we have of getting that. Okay. And even without the word net in there, we'd actually be okay if you go take a look at this graph, because this graph never reaches below the x-axis. So from -1 till +3, it really will just be the total of its areas between the x-axis, and this doesn't go below. Okay. So tomorrow when you come in, or the next day that I see you, we'll be working again on going over this, talking it through, but tonight you have 6-2 day 1 homework.